Hello, and welcome to Business Calculus Rates of Change. The study of calculus is based around two very important questions. The first one of those questions is finding the equation of a line tangent to a point on the graph. As we see right here, there is a straight line that touches the graph only once in a region close to that point. And determining the equation of that line can tell us some important properties about the functions near the point where that line intersects. The second basic problem of calculus is to determine the instantaneous velocity of some falling object. If you decide to jump out of a perfectly good airplane, after a little bit more study in this course, you will be able to determine the exact velocity at which you are plummeting to your doom. Both this and the previous problem can be solved by using a new calculus idea called the derivative. Fundamentally, a derivative is a rate of change, and to prepare to study it, we're going to talk a little bit more specifically about kinds of rates of change. Suppose you're traveling on a highway and pass mile marker 150 at 8 a.m. and then pass mile marker 290 at 12 a.m. The average rate of change of distance with respect to time is 290 minus 150 divided by 10 minus 8, which gives you an average rate of change of 70 miles per hour. It might be the case that you were traveling exactly 70 miles per hour at one point in your journey, but you weren't traveling exactly 70 miles per hour the entire time. The reading on your speedometer, which tells you exactly how fast you're going right now, is an example of an instantaneous rate of change. We're going to be discussing these rates of change in several different situations, including ones that don't actually involve velocity as we move forward. Let's define officially average rate of change. The average rate of change from x equals a to x equals a plus h is given by the following expression. F of a plus h minus f of a divided by h, where h is some non-zero number. H represents the distance between where I started and where I finish, and I'm measuring the average rate of change traveling between those 2 points. This expression is referred to as a difference quotient. Let's look at an example that doesn't have to do with velocity. The revenue in dollars from the sale of sod pieces is given by the expression R of x equals 40x minus 0.04x squared, where x is a value between 0 and 1,000. What is the change in revenue if production is changed from 100 pieces of sod to 400 pieces of sod? And what is the average rate of change in revenue for this change in production? The change in revenue is given by the difference between the revenue at 400 units minus the revenue at 100 units. By plugging 400 and 100 into our function and taking the difference, we see that we get 40 times 400 minus 0.04 times 400 squared minus 40 times 100 minus 0.04 times 100 squared, which simplifies to 9,600 minus 3,600, which gives us $6,000. The average rate of change of revenue for this change in production is given by the difference quotient. The difference in the final revenue minus the initial revenue divided by the final production value minus the initial production value. So R of 400 divided by R of 100, all over 400 minus 100, which gives us an average change in revenue of $20 per unit. Now let's look at an example that does have to do with velocity. A small metal ball is dropped from a building and will fall y feet in x seconds, as described by the following equation. 16 times x squared. We would like to find several things. The average velocity when x equals 2 and when x equals 3 seconds. The average velocity from when x equals 2 seconds to x equals 2 plus h seconds, where h is some non-zero number. We would like to determine the limit of the answer from part 2 as h approaches 0, assuming the limit exists, and talk about what the result from question 3 means. We use the distance formula to help us determine average velocity of this object. Distance equals rate times time, so if we solve it for r, we get that the rate of travel is equal to the distance traveled divided by the time elapsed. This allows us to look at our final position, f of 3, minus our initial position, f of 2, divided by the change in time, which is 3 seconds minus 2 seconds. Plugging in our values 3 and 2 to our function, we get 16 3 squared minus 16 2 squared all over 1, which is 80 feet per second. Here we use our average velocity formula in the form of a difference quotient. F of 2 plus h minus f of 2 divided by h is equal to 16 times 2 plus h squared minus 16 times 2 squared all over h equals 16 times the quantity 4 plus 4h plus h squared minus 64 all over h. Distributing the 16, we get 64 plus 64h plus h squared minus 64 all over h is equal to 64 plus 16h, which we get after noticing that 64 minus 4 is 0, and that we can divide out a factor of h. We can now take the limit as this expression goes to 0. We have the limit of our difference quotient, which we know from the previous slide is the limit as h goes to 0 of 64 plus 16 times h. Since this is just a polynomial function, I can plug in h equals 0, and we see that the rate of descent is 64 feet per second. The average velocity calculated over smaller and smaller intervals approach the value 64 feet per second. This gives us an exact measurement of the falling velocity when x equals 2 seconds and represents an instantaneous rate of change. An instantaneous rate of change between the points x equals a and x equals a plus h is given by the limit of our difference quotient, the limit of the average velocity as h approaches 0. So as the time interval that we are calculating our average velocity becomes smaller and smaller, we approach this instantaneous measurement. All right. What I would like for you to do is, using the example of the falling metal ball, find the average rate of change between x equals 3 and x equals 4 seconds, and the instantaneous rate of change when x equals 3 seconds. Here are some potential responses. And I would like to thank you very much for listening.